Pretty well everybody, when they start out in computer science, thinks that if your program is running too slowly, what you need is a faster machine. But some problems scale so fast, it is virtually impossible to keep up with them. That is the sobering reality at the heart of complexity theory. How do we embrace this fact? How do we deploy mathematical ideas to design useful algorithms for everyone? Google, for example, is essentially an algorithm to quickly find and rank web pages based on surprisingly sophisticated mathematical ideas. Our Turing machine is a robust concept to build a theory of speed of computation. Let's look at a simple example of how this can work out using the example language 0 and 1n. Here's a high-level description of the Turing machine algorithm. On input string w, the Turing machine M1 will firstly scan across the tape and reject if a 0 is found to the right of a 1, which just means that all zeros should occur before all the ones. We can think of this as a pre-processing step before moving on to the main part of the algorithm, which starts at step 2. Repeat until both some zeros and some ones remain on the tape. We scan across the tape, crossing off a single 0 and a single 1. So a pair of 0 and 1 will be crossed off in every iteration of this loop. Then finally, if zeros still remain after all the ones have been crossed off, or if ones still remain after all the zeros have been crossed off, reject. Otherwise, if neither zeros nor ones remain on the tape, everything has been crossed off, no symbols remain, then accept. We can think about the efficiency of this algorithm by linking it to the input size. Suppose we have an input string of size n. Then we can ask, how many elementary operations does it take to arrive at the answer? So we first need to ask, what are the elementary operations? They are a combination of moving one cell to the left or right and reading or writing to a cell. So in any one operation, you could move, read, or write, or any combination of the three. So now we can run the algorithm and count the number of elementary operations. So suppose we have the following input. On the tape of the Turing machine. The input consists of some n number of zeros followed by n number of ones. And now we have to run the algorithm M1 on this input. Step number 1 is that the algorithm is going to check whether all the zeros are before the ones. Or in other words, no zero should occur after a 1 has occurred on the tape. Okay, so you can see that the Turing machine has to make one pass over each of the cells of the input, going all the way till the end of the tape, and that will be enough to check whether all the zeros occur before all the ones. So how much time is that going to take? Well, that's going to take O of n time, where n is the length of zeros as well as the length of ones. Total length of the input is 2n, and in terms of big O, 2n belongs to big O of n. And so this first step takes big O of n time. Then the second step is where we have the important part of the algorithm, where we iterate over each pair of 0 and 1 and cross them out as a pair. So we are going to basically cross a 0 and a corresponding 1 And so this one operation of crossing out a pair of 0, 1, how much does that cost? So we have to cross out a 0, that's just one operation, and then travel along the tape until we reach a corresponding 1 and then cross out that 1. So this thing is taking O of n time, and then we have to move back until the first uncrossed 0 and then repeat the same process. So moving back takes O of n time, and then crossing the 0 and moving forward also takes O of n time, which together is O of n, and hence crossing off any one such pair is O of n time. Well, we have to repeat this process n times, once for every pair of 0, 1 on the input, and so we repeat n times. In total, step 2 is n squared, because we're running an O of n operation n times. And once all of the pairs of 0, 1 are crossed off, well, that's it, we're done with the algorithm. If all the pairs have been crossed off with neither zeros nor ones remaining, then we know that the input string is part of the language. So how much total time did the Turing machine take? Well, we can just add up the total times that were taken in step 1 and step 2, and so that is 0n plus 0n square, and the leading coefficient and the bigger coefficient is n squared that will dominate. This is just equal to O of n squared. In general, we can say that a Turing machine works in big O of fn time if it performs big O of fn elementary operations on any input of size n. We are now ready to define the time class of languages. A language belongs to time of t of n if it is decided by a big O of t of n time deterministic Turing machine. So the time class is a class of languages that we have defined in terms of problems decided upon by Turing machines. I will often use the word language and problem interchangeably. You should think of them as the same concept as far as the course is concerned. A language is a set of strings whose membership can be decided by a Turing machine in some amount of time. What the Turing machine is really doing is solving a problem, the problem of membership for each string. The amount of time that it takes in the worst case is the overall time class, capital TIME, to which the language belongs. Observe that there is an infinite hierarchy of time classes, each class contained within a bigger one. For every time class, there is another time class larger than it, which contains it.